Hey guys! We're Esther, and we're going to talk to you about energy diagrams. So first we're going to talk about Gibbs free energy, so that's the total amount of energy that's in a system. And the formula for that is delta G equals delta H minus T times delta S, which is enthalpy minus temperature in Kelvin times entropy. And first we have endergonic reaction, so that's when the reaction favors the reactants over the product. So the delta G, or the Gibbs free energy, would be positive and it's non-spontaneous. And then we have exergonic, where it favors the products instead of the reactants, and delta G is negative and spontaneous.
Equilibrium on an energy diagram refers to the point where the net force acting on a system is zero, meaning that the system is at rest. So on this diagram, the rate of A and B decrease, so the collisions between A and B will occur less. So then on C, the rate for C and D will increase, so the collisions between C and D will occur more often. Eventually, like I said earlier, the reaction rates will be equal. And then the formula for equilibrium for the Gibbs free energy is the negative rate times the natural log of the equilibrium K constant.
So now we have exothermic and endothermic. So exothermic and endothermic reactions are to do with enthalpy, or the delta H of a reaction. Exothermic, it's going to have a negative delta H because your energy starts up here and ends down here, which is less than where it started. So it's going to lose energy to the surroundings, and it's going to transition potential energy to kinetic energy. And then we have endothermic reactions, where the system gains energy from the surroundings, or gaining heat, or the surroundings are going to feel cold, and then its delta H is positive, and this is because the energy starts lower than when it ends, meaning it has to gain energy, and it transitions kinetic energy into potential energy. Now we have transition states and intermediates. So first, a transition state is the highest point of energy on each peak, and it is normally, like if you were to quantify it in a reaction, you have the starting thing, the ending thing, and then here, you're gonna have both of like where it's like switching in like a reaction, kind of attached to it, partially pulling a negative, or no, partially pulling a negative. It's kind of like the in-between state. And then intermediates are gonna be another type of like in-between state, but at the same time it's lower area, because then you have to reactivate it in order to get it to go to the end. So this is an example of an intermediate. This is a carbocation intermediate, and generally what we most see in organic chemistry.
Thanks for listening to our talk about energy diagrams. We hope that you learned something.